Good. All right, hi everyone. Glad to be here. So I'm kind of picking up a little bit where John left off, talking about okay, we have this Thor-Soar agent that can do a bunch of things. How can we maybe extend some of its capabilities using interactive task learning? So this is kind of some initial work informed by things I did during my doctoral research with Rosie, if you're familiar with Rosie. And so this is kind of some initial work looking at how we can do this in Thor-Soar. So if we think about an agent, it's going to have some initial task knowledge, but we want it to be able to improve its performance over time. Okay? And so we want it to gain additional knowledge as it interacts and works with the world. And we've heard kind of a lot of different ways you might do that. John talked about maybe doing some exploration or experimentation to figure things out. We've heard about maybe could we use a knowledge base, an external knowledge base. I think James may have done this before, using an LLM to like gain knowledge. But we're going to focus on a really powerful one, including the one I'm doing now, which is instruction. And instruction is a highly effective learning source, delivers high quality knowledge, the ability to contain feedback and corrections to what you're teaching, can leverage a lot of domain knowledge, and it's very efficient with data examples, able to contain, enable rapid learning. And so the goal of kind of this problem of interactive task learning is to design agents that can learn new tasks from scratch through natural forms of interaction. And we kind of have focused on a specific flavor of this, which we call situated interactive instruction. Situated meaning that you and the agent are in the same environment, being able to interact with each other. It's interactive in the sense that both the instructor and the agent can initiate new dialogue and new questions. And then we're focused on instruction. That's natural language instead of the demonstration or other things like that. And kind of a key aspect of this learning problem, why it's like challenging but also powerful, is that the agent must learn quickly from few examples, right? This means the learning must be very efficient. It must be able to generalize quickly. It must be able to compose knowledge together. And it has to be able to learn of diverse types of knowledge. So that's kind of like background. You've probably heard me talk about this before. So let me kind of talk about steps in Thor-Soar and what that might look like. So we've seen, kind of John showed off some examples of this domain. And everything he talked about kind of forms this initial knowledge that the agent has, right? How to manage the world, recognize objects, some natural language comprehension, do these actions, and this whole host of planning using means ends analysis. So that's obviously a lot. So let me just kind of go through an example, breaking down how it would go if I tell the agent to pick up the apple, what happens? So it goes through a comprehension step, language comprehension using some work of Peter to create a message structure. I'll simplify this just to make it clear. We get, okay, the person's telling me a command to pick up, and then this specific apple, which is grounded in the world. And then it goes to interpretation. Okay, I have this message. What should I do with this? And this is kind of what John was talking about, where a difference is that instead of mapping this onto an action or an operator, we're going to map this onto a goal or a desired state that we want. And that's our interpretation phase. So what we're going to use is this knowledge in semantic memory, this kind of network describing this action of pickup, where we have kind of two parts of it. We have the structure of the action as given through the message or given as a command. And then we have how we connect that to a description of the goal or a set of desires in the state. So this kind of forms our network that it starts with. And so the agent takes this, this command, this message structure. It uses this network to kind of map it together, and it constructs a goal. In this case, that, okay, my desired state is that I'm holding this specific object. And then what kind of everything John talked about can take over. The agent can use planning and execution to have steps that achieve this goal. So a kind of a motivating question we like to ask then is, what happens if the agent doesn't have this knowledge, right? What happens if the agent doesn't have this network? Can we learn it? Can we learn it through instruction? So imagine I tell the agent to discard the apple, and the agent doesn't know what this means, right? So it's going to go through comprehension, it's going to get this message structure, and then it's going to reach a failure because that knowledge isn't in estimate, right? It doesn't have a representation of this network. So it's going to ask a question. It's going to ask, okay, what is the goal of discard? And the structure can reply something like, okay, the goal is that the apple is in the garbage can. So this message gets goes through comprehension, and we get some representation of this goal structure that the apple is in this garbage can. So we can now start the learning process. So we have these kind of two pieces of knowledge. We have the command, the message, and then we have this goal, and we're going to use them to create this network in semantic memory. And we do it in a fairly straightforward way. We kind of just record the structure as we see it. But then when it comes to the goal, we have this, okay, there's one desired, it's a relation, it's using in something. But then the question is, how do we generalize the arguments, right? And we use kind of a straightforward approach. Basically, we see, okay, what objects in our goal appear in our message? And so in this case, the apple appears in both the goal and the message, or in the command. And so we're going to say, okay, we're assuming we can generalize that, right? And we call this like an explicit argument. And so you notice that in the network, both of these things map to the same slot. It's kind of a placeholder for this object that will be discarded. But the second thing, the garbage can, is only in the goal, and we call this an implicit argument. And so we're going to try to extract like some kind of default representation that we can use to recognize or to instantiate this in the future. And we use some of the language in the referring expression to be a little bit clever. And we'll say, okay, I'm going to assume that my goal is to put it in something that has category garbage can. That allows it to do a little bit of generalization. So if after that learning episode happens, I say something like discard the potato, it's able to kind of do the same thing, right? Using that network that we learned to create, to instantiate a goal, which can then the agent can satisfy using its planning. So that's kind of the basics of this initial approach. So what can we learn? What are kind of the current capabilities? So again, this is kind of some early work. So the agent can learn goals composed of one or more property, relation, or holding desires. So I haven't shown it here, but we could, for example, serve the potato. We could learn a goal is that the potato is cooked and the potato is on the plate. So that's more than one. So here's just a couple examples. It's able to do some generalization. It's able to learn from a single example, which is nice. However, that kind of leads to a goal, which is that it's good at generalization, but maybe it's too good at generalization, right? It's going to assume in the example I showed that if I want to discard anything, it goes in a garbage can, right? Whereas like maybe I want aluminum cans to go here, or maybe I want a mug of water and empty that out of the sink. So where in like Rosie, we did really aggressive generalization. I think maybe we're going to look in the future, being a little bit more cautious about that, depending on the type of objects. Currently, they're limited to these kind of goal-based descriptions of tasks, and there's no goal variations yet. Like I said, of if we want to teach something like store, we want it to store maybe an apple in the fridge, but store the plate in this cupboard and store the knife in this drawer. So then kind of moving from here, what are some next steps? And again, we kind of ask this question, all right, we require a lot of this initial knowledge. So can we maybe learn, for example, knowledge about its basic actions, and can we start to learn this? Things like preconditions of an action, effects and side effects, preferences and search knowledge, and we've already started some initial work in being able to learn some of these MEA proposals that John mentioned. But that's everything I have. Everything I have for today. Have any questions if we have time?
I have a question. I'm wondering, like, if it is possible, like, to put larger models in those, um, I would say out of the distribution problems to test if, use larger models as a bridge to generate new production rules of Soar, then translate those production rules into the Soar syntax and, to tackle those new problems. Is it a possible approach?
So, kind of a general approach that we use is, we get knowledge from instruction. So knowledge comes from the instructor, comes into the agent. We interpret that knowledge. We usually put it in semantic memory, and then while the agent is doing processing, it retrieves that knowledge. It can use that to learn chunks. And so the source of that knowledge, like we typically think about instruction, but we've also looked at, like, could we get that knowledge from an LLM? So instead of asking a person, like, what's the goal? Asking an LLM, what's the goal? And then I translate that into kind of SOAR representations. And then we could learn certain kinds of chunks like we do in this case.
So I'm just going to interject. What Aaron just talked about was a way where we do not generate SOAR rules directly from LLMs. So our view, I don't know if it's a philosophy or whatever, but we don't want to depend on the LLMs knowing SOAR syntax, or and it's not like when a human interacts with an LLM or interacts with a system, it generates neural structures that it injects into your brain. And that's sort of what a rule is for SOAR. So we're trying to get the knowledge in the most general way. And I think you'll see a lot of examples of that in James's talk.
Yeah, but I do think it's worth considering using a language model to, once we have a template of a rule for a instance, it could help us with generalizations to other instances, I think, especially if all it's doing is doing a few changes. I think that's an approach we're looking into.
I see. Thank you for the nice discussion. I really appreciate it.
Go ahead.
So one of the things that I thought about before with Rosie, and that maybe is a little bit just more obvious today, isn't part of the problem that you're trying to learn language and instruction at the same time? Like your example of overgeneralization from discard, right? If I knew discard and throw away and recycle and compost as verbs, then if somebody said discard, I would have a cue right away that, oh, that's a kind of general thing, and there's all these instances of it. And so it seems like that's part of the challenge here.
Yeah, I mean, we've talked a little bit, kind of this idea of maybe one of the research directions we want to go with Thor-Soar is this kind of like, what if instead of one canonical way of thinking about a task, like we have lots of variations of it depending on things like the types of objects and being able to handle things like, these variations. It's not just like discard is this one thing, but we have like recycling, we have discarding, we have pouring things out, emptying, all this. It's like a much more challenging problem, but I think could be really interesting.
Great. Thank you.